Hi everyone, let's go through the week 6 course notes where we're doing some mutually exclusive events and also some independent events. So firstly, what was mutually exclusive event, or what was a mutually exclusive event? We talked about it last week, and it was events that cannot happen together. So let's look at a really simple example, tossing a coin. And the events I'm going to talk about are I could get a head or I could get a tail. Can I get a head and a tail? No, they're mutually exclusive events. They're probably getting a head, probably getting a tail. So if I were to draw them in a Venn diagram, well, again, pretty simple. I'd be saying I could get a head or a tail, but there's no overlap. There's no head-tail zone, tossing one coin. That's why this diagram down here we'll discuss in a sec. There's no intersection with mutually exclusive events. They can't both happen. Okay, let's look at this statement here. This statement here is saying the probability, well, let's talk about, instead of A and B, let's talk about H and T. That says the probability of getting a head or a tail is equal to the probability of getting a head plus the probability of getting a tail. So for a mutually exclusive event, that's the first thing we're trying to convince you of. That the probability that I toss a coin and get a head or a tail is equal to the probability of a head, which is 1 in 2, plus probability of a tail, which is 1 in 2. Half plus a half is 1. Okay, and do you agree that the probability of getting a head or a tail is 1? That I must get one or the other? Absolutely. So simple situation, but there it is. It's basically saying that an or in probability is like a plus. Okay, what's the probability of this happening or this happening? Just add the two together. Okay, the individual probabilities, as long as there's no overlap. If there's an overlap, as in if they're not mutually exclusive, there's a slight complication. It's not too bad, but that's the next page. At the moment we're just keeping it simple. So let's use this next example. Yeah, the next example will do. Let's look at this example and then try and make sense of all of this stuff. Okay, firstly let's just look at what's happening. There's a barrel with 44 balls in it represented in this Venn diagram. Okay, 10 of them are green, 7 are blue, 27 are other. If a ball is selected at random from the barrel, what is the chance it is either green or blue? So the events we're talking about is it's green or it's blue. And there's no overlap, okay? I can't pick out a ball that's both green and blue. They're single color balls, okay? It's green or blue, no overlap. Great. Okay, let's look at this first little statement right here. It says N of A union B equals N of A plus N of B. Let's first see what that's saying. That's saying the number of elements in the union of A and B is equal to the number of elements in A plus the number of elements in B. In other words, the number of elements in the union formed between G and B, in other words 17, is my total of stuff in the union of these two, is equal to the number that was in the first circle plus the number that was in the second circle. Absolutely. If there's no overlap, the sum of what's in both circles is the sum of one circle plus the sum of the other circle. Okay, hopefully that's a nice one. Now, then they're trying to go on to this next thing. So then the probability of A union B, so in other words, in this example, the probability of green union blue, they're saying is equal to the number of ways you can get a green or blue ball over the number of ways I can get an outcome, as in what that really means is the number of elements in the set of A union B over the number of elements in the sample space. And the number of elements in the sample space is just the total number of outcomes. In this case, well, there's 44 balls. And how many balls are there that's green or blue? 17. Now this next bit is saying that, well, N of A union B is the same as N of A plus N of B, which is what it already says up there. Note, big important note here, what I'm doing here, this whole thing in this circle is extra nerd information, okay? I mean, it's great if it makes sense, it should be a logical progression, but it's just us justifying that this first statement is correct. So the whole moral of this first page is going to say or is like a plus in probability, okay? There's the big outcome of this. Let's keep going through and seeing what it's saying. The next step says instead of writing N of A union B on top, I could have written N of A plus N of B. Well, in this case, it's N of G plus N of B, which is a 10 plus a 7. Would you agree that 17 on 44 is the same as 10 plus 7 on 44? Yeah, that's how we got the 17. Then it says if I've got the same denominator, I can split this fraction up into two bits, NA on NS and NB on NS. Well, we don't deal with fractions much and we've got a calculator anyway, but it is true what they just said. 10 on 44 plus 7 on 44 is the same as the previous line. You just add the numerators when you got the same denominator. And the last step says that n of A on n of S is just the probability of getting the first event, which is PG in this case, plus PB. Would you agree that PG, the probability of getting a green ball, is 10 out of 44? Yeah, there's 10 of them out of 44 total. The probability of getting a blue ball is 7 of them over 44. Yep, okay, so that was more mathematical proof, but it all came down to the probability of two events. The union of two events occurring is equal to the probability of one event plus the probability of the other event, as long as they're mutually exclusive. So what's this big issue with, well, what if they're not? What if there's some overlap? Well, let's look at an example where there's overlap. We call it intersecting events. Overlap is an intersection. Just these circles intersect each other and form an overlap. Let's just look at this example and we'll use this to explain how the formula is going to change. It's a very minor change. Basically all of this page is about this formula I just put a box around. It's saying that if they were mutually exclusive on the first page, this part of the rule didn't exist. The first page said probability of A union B is probability A plus probability of B. What this page says is, if I get my eraser thing going, that probability of A union B is probability of A plus probability of B. I'm really struggling to talk today. This is a good day to make a video. Minus the probability of A intersection B. Now that looks pretty hard, but we'll make common sense of it. Let's find out. This example is talking about just rolling a single die. And the outcomes I can get are 1, 2, 3, 4, 5 or 6. Now event A that's being discussed is that I get an odd number. So the event A in the circle has 1, 3 or 5. They're the only odd numbers out of 1, 2, 3, 4, 5, 6. Event B is that the number is less than 4. Well, how many numbers are less than 4 in 1, 2, 3, 4, 5, 6? Only 1, 2, 3. So if we go through the numbers individually, 1 is odd and less than 4, so it's in the overlap. 2 is less than 4, but it's not odd, so it's only in the less than 4 part of the circle. 3 is odd and less than 4, so it's in the overlap. 4 is neither odd nor less than 4. 4 is not less than itself. 5 is not less than 4, but it is odd, so it's in the odd part of A. And 6 is neither odd nor is it less than 4. So the Venn diagram's been filled out correctly, and yes, we have an overlap. So if someone asked me, what is the probability of A union B? Firstly, let's ignore the formula. Let's do it manually. Manually, I look at, well, the probability of me rolling a die and getting an outcome that's in the union of A and B is saying, well, there's 4 outcomes in the union, there's 6 outcomes all up. So my answer is 4 on 6, which is 2/3 if I simplify the fraction. There's 2 2's there, there's 3 2's there. So my probability of A union B is 2/3. Now let's look at the formula. The probability of A union B, supposedly, for non-mutually exclusive events, as in intersecting, is the probability of A plus the probability of B minus the probability of A intersection B, which is what it says down here. Why? Well, what's the probability of getting an event out of A? There's 3 events in A, so that's 3 out of 6. Plus, what's the probability of getting an event in B? Well, there's 3 events in the B circle as well, so that's 3 on 6. And then it's telling me to subtract the probability of getting something that's in the intersection. How many things are in the intersection? There's only 2 things in the intersection. Why do I need to subtract the intersection? And here's why. I'll just erase for a sec. When I counted up the number of things in the A circle, I got 3 things. That thing, and that thing. Then when I counted up the stuff in the B circle, I also got 3 things. But look, I'd already counted 2 things. So I shouldn't count those 2 things twice. There's only a single 1 and a single 3 as options for rolling a die. So what this is saying is, sure, add A and add B, but you just used the overlap. You just counted 2 twice. So take off a 2. Now, I hope I'm explaining it well, but it's like, I like this example. I'm sure I've got something coming up. Say I check a class, and in the class we've got, so I've got 12 students that do maths. So I asked everyone to put their hand up if you do maths. I saw 12 hands. I asked everyone to put their hand up if they do English, and I saw 10 hands. And then I counted up the class, and there was only 15 students. I went, hang on, well, that's like last week. Now what happened? All it means is there must have been an overlap. Some students put their hand up twice. Because if I add it up, and let's say that I asked who did neither maths or English, and it was nobody. So I've got, I could do a better Venn diagram than that, maybe with room to draw numbers. So let's say that's maths, that's English, and no students did neither. So I'm trying to say I saw 22 hands raised out of 15 students. And last week we would have said, well, that gap of 7 means 7 people that did maths must have also done English. That's why I seem to have 7 more students than I really had. So the overlap was 7. The rest of the maths circle would be 5 because it got out up to 12. The rest of the English circle would be 3 because it got out up to 10. And let's look if I've done everything right. This is very much last week content, week 5. Maths is 10 people. It's 12 people. Good sums, David. English is 10 people. Yep. 15 students all up. 5 plus 7 plus 3 is 15. And as I said, no one did neither. All right. Now let's look at the logic. If I said, what's the probability of event M union B, and try to use the formula, well, I'd say it's the probability of getting someone out of the M circle, which is 12 out of the 15 students, plus the probability of getting someone out of the, I can't even read my own writing, it's an E. The probability of getting someone out of the E circle is 10 out of 15, but look, I just counted those 7 people twice, so I better subtract the probability of the overlap, not twice but once. I've got 2 7s in there, I'd better take one of them out, and that ends up being 12 15ths plus 10 15ths, that's 22 15ths minus 7 15ths is 15 15ths, which is 1. Yes, I've got a probability of 1 of getting someone within the union of M union E because there's no one outside of it. So this works. All we've got to think of is if there's an overlap, don't count it twice, subtract one of them off, one of the overlaps off, so it was not counted twice. Okay, so there's that example to go through. Now the next bit, multi-stage experiments with equally likely outcomes. In this section we consider experiments which involve combining a number of different stages. Okay, I'm going to do this, and then I'm going to do this, then maybe I'll do something else. So it's just multi-stage. We've just been looking at, look, I did this one thing, what's possible, now I'm going to do more. And a nice way to do it is tree diagrams. Tables are good too for some, as long as I've only done 2 things. If I get into 3 things, we've got to go back to tree diagrams. But let's look at both here. There's both a tree diagram and a table here for a situation where we talk about tossing of 2 coins. Now let's look at this introduction. For multi-stage experiments, we use a notation P of AB to mean the probability of event A happening at first and then event B happening in the second. So unlike algebra, I know algebra, AB and BA are the same thing, but in here, the event, or the probability of the event AB happening means A, then B. Okay? The probability may be the same or may not be the same of getting B, then A. Depends what we're discussing, okay? In this case, they're equally likely, so it's not going to make much difference, but sometimes it will make a difference, okay? But just note that when we've got 2 letters, we're saying the first event happening, then the second event happening. All right, that's a slow way to do it. So here's a first event happening, first toss of the coin, and the tree diagram, we've got these branches. I always start with a point, and there's only 2 branches here because there's 2 outcomes. There's as many branches as there are outcomes. But in first toss of a coin, I could go heads or I could go tails. Now let's pretend we got a head, and I'm going to do the second toss. Well, then there's still 2 outcomes. After I got the initial head, I could still get another head, or I could get a tail. Or after the first head, a tail, I could have got a head or a tail. So you can see we end up getting 4 unique outcomes. okay, unique in order anyway. I could get a head then a head, a head then a tail then a head, or a tail then a tail. Now, we've got to watch our wording here. If some question said, look, what's the probability of tossing 2 heads? Great. It's only 1 outcome out of 4 outcomes. So there are 4 unique outcomes. Head is one of them. So that'll be a probability of 1 in 4. In fact, they're all probabilities of 1 in 4 because it said equally likely outcomes. There's no bias coin. This would all change if I did a bias coin. If I said, look, this is a coin where heads only came up a quarter of the time, but tails came up 3/4 of the time, then I'd have to do what we'll do next week, which is where we have to draw probabilities on the arms because they're just not equal. And then I will still have 4 unique outcomes: head then tail then head, or tail then tail. But the probability of heads is not 1 in 4 here because they're all different. Next week we'll say the probability here is going to be a quarter times a quarter is a 16th. So I won't go ahead and do that. I'll just say, look, at the moment we're looking at equally likely outcomes. I don't have to write any of these probabilities on the arms because they're all equal outcomes. So since they're all equal, every final event after doing it, this thing, and this thing are all equally likely. Okay, so same with the table. Well, a table implies that all the outcomes are equally likely. We're not going to use them next week in bias stuff. And again, a table summarizes it. If this is, say, the first coin, and this is the second coin, maybe I got a head on the first and second, maybe I got a head on the first, but tail on the second. Tail on the first, head on the second, or tail on both. Okay, so both diagrams are great. And they're all talking about equal probability in the final 4 events. Like if I said, what's the probability of getting, let's be clever, of at least 1 tail? If that was my question, and so I looked at the table, at least 1 tail means I want 1 tail or more. It means give me everything, but don't give me no tails. Has head tail got at least 1 tail? Yep. Hello, Nathan. Has tail head got at least 1 tail? Yep. Is 2 tails at least 1 tail? Yep. Yeah, mate. Hang on. Well, we've got 3 out of 4. I think we're getting told. It's 2:35. It's not dinner. Pause. And we're back. We're fed. Okay. So in that example I was saying, there's a 3 in 4 chance of getting the probability of at least 1 tail because 3 outcomes satisfied it and only 1 of them didn't, but 3 out of the 4 satisfied it. So there's a nice example of equally likely outcomes. Let's look at the next one. It gets worse, a die and a coin. Here, well, you might have to do either. I tend to prefer the tables when there's coins involved, especially if it's 2 coins. Do you really want to do a tree diagram with 2 coins? I'd have to do 1, 2, 3, 4, 5, 6 arms. And then off each of the arms, I'd have to do 1, 2, 3, 4, 5, 6, because I could get a 1. I could get another 1. Okay, you can see there that it's going to be rough. You can also see that, well, if that 1 could then have 6 outcomes, 2 could then have 6 outcomes, 3 could have 6. There's actually 36 different outcomes, 6 by 6. So yeah, that's a bit intense. I would rather use the box in that case. If I was talking tossing a coin, rolling a die, I would say maybe here's the first die, 1, 2, 3, 4, 5, 6, and I'd have a grid thing. Second die, 1, 2, 3, 4, 5, 6. I'm not saying I'd be stoked about doing this question, but I'm saying that I would do it like this. And again, there's 36 outcomes, all just represented by a grid. So let's just, while we're at it, let's just make up a question associated with this. What's the probability of rolling a sum of, say, 8 will do. I'm rolling 2 standard dice, and I want to know what's the probability of rolling a sum of 8. Okay, well this grid will help me, because that every single one of these little boxes in the grid is a potential outcome. My probability is going to start out over 36. How many total? 8. Well, I could get a 6 and a 1. I could get a 6 and a 2. That'll do it. What about a 5 and a 3? That'll do it. Or a 4 and a 4. Is 3 and a 5 different to 5 and a 3? Yeah, it is. That's the first die. That's the second die. So there are 2 unique ways of getting 3 and 5, or 5 and 3, to make that 8, and then a 2 and a 6. So what have I found? 1, 2, 3, 4, 5 of the 36 outcomes are ways to roll an 8, or a sum of 8, when you add up the 2 numbers on both. So there's my probability, 5 on 36. We'll get asked questions like that. Well, it's not a promise, but I'm pretty confident. That grid is the way to go. Okay, tree diagram, will work, but so let's go back to the one that's not as bad, a die and a coin. Okay, we're back. Had a bit of a power failure there. Okay, so we just looked at 2 dice and making a table for it. You can see for the example at the top of this page, we've got, what about if it's only 1 die and 1 coin? Well, there's 6 separate options for the 1 die and only 2 for each coin. So for every of the 6 branches, we've got 2 more. So you can see there's 12 all up. Or whether I do it in the table, it's a 6 options by 2 options. So you can still see we've got 12 unique outcomes, all of the same probability. So for the question given, what's the chance of rolling a 6 and tossing a head? You can see it's 1 in 12. We've only got the 6 on the head, and yeah, 1 out of the 12. Or, you know, you could get asked maybe, what's the probability of getting, hello Nath, you're back already. Oh no, don't, that caused the last power issue. What about getting say a head and an even number? Well, still, I could go, here's a head and even number. Okay, back to what I was saying. You might ask, what's the probability of getting, say, a head and an even number? Okay, well, a head and an even number, it's got to be in the heads column, it's got to be the evens. So say I got asked that, my table really helps me. Or it doesn't matter if I use the table or the tree diagram. But with the table, I can see there's 3 outcomes out of 12 outcomes which satisfy that question. So, tables and tree diagrams, great. So, we need to look now at independent events, which, well, they're called independent of each other if the probability of one event happening is not influenced by whether or not the other event happens. So, with the above example, say I rolled a 3. Did that affect what might now happen with the coin? No, they're totally independent. So we're already looking at an independent event there. Well, what's an example of non-independent then? Well, say, like here, the cards example. If I've got a pack of 52 cards, there are 13 hearts in it. And if say I say, well, what's the probability of picking out a heart? Well, it's 13 in 52. Now, what's the probability after picking out of a heart of picking another heart? Well, now there's only 12 hearts and 51 cards. So it mattered whether I got one or not. Because if I didn't get one on the first roll, or first choice, there's still 13 hearts, but only 51. So they are not independent events. I needed to know the outcome of getting a heart or not getting a heart before I could tell you the probability of the second one. So some events, and it'll be just common sense, you can work out whether the first event affects the second one, or maybe it doesn't. So let's look at our example on this. Now, our example on this is going to involve multiplication. Now, I already went into this one before. I said I was doing it a bit early. Well, here it is. It's caught up with us. I talked about a dodgy coin where heads was a 1 in 4 chance and tails was a 3 in 4 chance. Okay, so, and then I said, well, if that happens, head, tails, interesting too, it's still 1 in 4, 3 in 4, and it's still 1 in 4, 3 in 4. So the independent event doesn't mean it's got anything to do with whether the coin is fair or not. It's just, if I get this wonky coin and toss it, does the first outcome affect the second outcome? Absolutely not. You're tossing the same coin. So it doesn't matter whether it's the first toss or the 5th toss. Every time you toss that coin, the probability is the same. It's a 1 in 4 chance of heads and a 3 in 4 chance of tails. Okay, so I said before in the other example, well, how do we work it out then? What's the chance of getting a head and then a head? And I said if I walked along this way, I would do a quarter times a quarter, which is a 16th chance of getting that outcome head-head. I multiplied them, and that's exactly what this is telling us to do. So far, earlier on we said if we're saying what's the probability of this event or this event, we said, well, I'll add them. If they were non-mutually exclusive, we had to take away one of the overlaps, but or was a plus. This is saying what's the probability of this event happening and this event happening, and we're timesing them. So I think of this in probability as or is a plus and is a times. In the same way, what's the probability of getting a head then a tail? Well, I'd walk along this tree diagram and I'd say, well, a quarter times 3/4 is 3/16 of a head tail. 3/4 times 1/4 is 3/16 of a tail head, and 3/4 times 3/4 will be 9/16 of a tail. And look how they all add up. 1/16 plus 3/16, that's 4/16, plus 3 is 7/16, plus 9 is 16/16. Yes, of course they add up to 1. All the outcomes have got to add up to 1. But okay, I used a tree diagram there for independent events, and the probabilities were the same on every, I call them, the V's, the branches. The probability was the same on each one, but I had to use a multiplication principle. If it was that and that, or that and that, or that and that, or that and that. And there's more of that next week. But let's look at the example we've got here. And we're using a table. Because it's 2 dice, I said before, I really don't want to do a tree diagram for 2 dice. It works, but it's just, a lot of effort. So let's just look at this. And I know I've got one written down there already. We'll just use that. It's been filled in for the third. But we can use the diagram, or maybe we don't need to. It depends how well we can picture what we're talking about. Look at the first question. We roll 2 dice, one after the other. What's the probability of rolling a 2 followed by a 4? Well, given that this tells us that the probability of, say, a 2, then 4, is equal to probability of a 2 times probability of a 4, again, because they're independent events, the outcome of the first roll doesn't affect the outcome of the second roll. So that's exactly what we're talking about. The probability of 2 then 4 is the probability of 2 times the probability of 4. Probably rolling a 2 is a 6. Probably rolling a 4 is a 6. The probability of those 2 times, 1 by 1 on top, 6 by 6 on the bottom, is 1 in 36. In other words, if we look at this picture down here and ignore those 2, how many outcomes are a 2 then a 4? On the first roll it's a 2. On the second roll it's a 4. Just the 1. Just one outcome out of those 36 boxes is a 2 then a 4, because it's separate to this one. The 4 then a 2, nope, he said 2 then 4. Remember we said probability of AB is A then B. It's not the same as BA like in algebra. Well, similar thing. Next question says what's the probability of odd then even? Alright, well by the same logic, that'll be the probability of odd times the probability of even. The probability of rolling an odd number, well that's, I could call it a half or 3 on 6. I'll just stick with 3 on 6 at the moment, because 1, 3 and 5 are odd out of the total number of options, 1, 2, 3, 4, 5, 6. And 2, 4 and 6 are even. There's 3 even potentials when rolling a die. So what do I get all up? I get 3 by 3 is 9 on 6 by 6 is 36. In other words, a quarter. So that's saying that I would have gotten 9 out of this box if I'd drawn it manually. Well, is that true? Let's look at it. Odd then even would have been first roll get odd, then second roll get even. Odd then even, odd, yep. A 3 then 2, a 3 4, a 3 6, a 5 2, a 5 4, a 5 6. Yep, 9 out of the 36. But I didn't actually have to draw the whole grid. But let's look at C, and I'll cross out this garbage. Garbage, David. Okay, a total of 11. Now this is where you could do it manually. Actually, I'll delete everything. Here's me doing it manually, and I've already written it down here. I've just got to think, in how many ways can I get a total of 11? There's actually only 2 ways. I could get a 6 then a 5, they add up to 11, or I could get a 5 then a 6. They're 2 different options. You can see in the diagram, here's 6 then a 5, here's a 5 then a 6. So you can already see the answer is going to be 2 out of 36, which is equal to 1 out of 18. If we did the formula, well that would say the probability 6 then 5 is probability of 6 times the probability of 5 is that. 5 then 6 is also 1 in 36, and as we said before, what do you get? What do you use with or as a plus? what's the probability of 6 then 5, or, don't close it, 5 then 6? Well, that's the probability of the 6 then 5 plus the probability of 5 then 6, which is 1 on 36 plus 1 on 36, which is 2 on 36 as we knew before, which comes down to 1 on 18. So yeah, whichever way you choose to do. In that case, I think it's much easier just to do a quick grid and find there were 2 outcomes out of the 36. Okay, I think we're done there. And we are. Okay, that made sense. A lot of stop and starts in that one. So it was not a good recording day. Okay, see ya.